Thank you, Louis, and thanks to the organizer for having me here. This workshop is very dear to my heart since long-range interactions pay for my living since 25 years, as Louis can confirm. So today I thought I would tell you something new that actually, at least the second half of the talk, I have never talked about, and I'm curious what you say. Yeah. So it's about dipolar interactions, of course, but not very cold. Yeah, so very hot means either room temperature or way above room temperature. Yeah. In my institute, we are working on long-range interactions in many different aspects. Yeah, a lot of work is going on in the ultra-cold, and you have heard about these experiments with the magnetic quantum gases. We also have an activity on ultra-cold Rydberg molecules and impurities. We even have, as many people, a quantum computing activity these days. But today I want to focus on this hot stuff, yeah, which is combining hot atomic and also molecular vapors with integrated electronics and integrated photonics. Let me start, as this has not been done here yet, just by the magic of Rydberg atoms first. I don't have to introduce this in this audience, but just to remind everybody, if we are exciting, for example, with 2 photons to a Rydberg state here, yeah, then we have huge interactions between Rydberg atoms, giving rise to the Rydberg blockade phenomenon that, you know, ever since it was proposed in 2000 as a mechanism for building quantum devices, keeps us busy still today. Yeah? And that is due to the fact that this van der Waals interaction, it's a C6 interaction. Yeah? It goes like 1 over the distance to the 6th power, scales with the 11th power of the principal quantum number. And if you do a decent control of your stray electric fields, this principal quantum number in our experiments at least can be higher than 200 or even more. Yeah? So that's a huge Rydberg orbit that can be as large as many micrometers, yeah, for the electron wave function. And it's, of course, a very fragile object. Now, this Rydberg blockade, of course, was demonstrated many times in the cold atom world. Some years ago, actually 10 years ago, we set out a project to see whether we can study and make use of the Rydberg blockade effect with thermal vapor cells. Okay. And if you look at this blockade mechanism in an ensemble of atoms that are not structured by any lattice or so, just somewhere in space, and you excite them, then due to this blockade mechanism, of course, you all know, yeah, the Rydberg excitations have to keep a distance, the so-called blockade radius. Yeah. This turns out to be a length scale on the orders of tens of micrometers in the ultra-cold and on the order of 1 micrometer, if you plug in the numbers, in the case of hot vapors. Because how do you calculate the blockade radius? Well, it's the interaction strength compared to the bandwidth of your excitation. Yeah? And if it is the Doppler width, yeah, instead of, let's say, the natural line width, well, then this blockade radius will shrink. But as this potential goes down like 1 over R6, it actually doesn't shrink that much, yeah? Just from 10 to 1 micrometer. So if you build a cell, a vapor cell, yeah, which with 1 micrometer dimensions, you should be able to use the blockade to build, for example, a single photon source, or to prepare one of these W states where you have a single excitation that is shared among many atoms in the ensemble. Yeah, and this is the original paper, of course, where you see that basically what you get is an effective 2-level atom, although it's an ensemble, where the excited state is this excitation that is distributed over all atoms in a coherent fashion. Yeah? We call it a superatom. Yeah? Although it's thousands of atoms, it behaves like a two-level system. If you combine this superatom idea with four-wave mixing, namely you go up to the Rydberg state and you go down maybe another route here, yeah, for example, D1 and D2 line in rubidium, then you produce, then you basically copy this quantum state, this W state that you have prepared in the Rydberg state to the light field and you can detect it. Yeah? Moreover, if this wavelength involved is smaller than the blockade radius, which is the case here, and you have an optically thick medium, this photon will come out in a directed fashion in the forward direction, and that makes it nicely detectable. And without going into any detail, just show you our self-made cells. Yeah? You can see that they are thin. Yeah? You see the Newton rings here. Yeah? So there are two glass plates. You can see here a stem where we are putting a little bit of rubidium. Yeah? And then with these Newton rings, you can actually measure the thickness while you do the measurement and make sure that your cell is thinner than the blockade radius. Yeah? Here is Harald and Robert filling one of these cells. Here's another example of these cells. We put this cell between two lenses to focus our excitation lasers down to below 1 micrometer, such that in all 3 dimensions, the volume where we excite is smaller than 1 micrometer. That's the schematic drawing of this. So the transverse size of this laser beam is smaller than the blockade radius, and the thickness of the cell is also smaller. And then in this particular example, we are exciting at the D1 line, and we are detecting at the D2 line. Yeah? We actually have a wedge cell, as you have seen. You can see these Newton rings. So when we move the cell, we can change the thickness. And that's already 5 years ago. We can then look at this emitted light in this four-wave mixing process and indeed measure a G2 correlation function that is not perfectly zero, but clearly below 0.5, meaning that this is a non-classical light source. The brightness of this source is about 10%, so it's a deterministic single photon source with a success probability of 10%. We can change the cell length from 600 nanometers to 800 nanometers. The blockade still works, but then at around 1 micrometer, the blockade stops, and the G2 function goes back to 1. So far, so good. Yeah. So this Rydberg blockade idea works even for hot vapor. Actually, here we had to heat the cell to 200 degrees, yeah, just to have enough optical thickness, yeah, because that's the figure of merit, optical thickness per blockade radius. And this cell was actually optically thick, although it was only a 1 micrometer or less in thickness. Okay. Now, if you want to integrate this into some photonic circuit, yeah, that would be nice, yeah, because it could be multiplied, and you would also think that these photons that are emitted are always the same photons, yeah, because it's rubidium. It's not a quantum dot or an NV center where you get different wavelengths for any defect or any dot. Yeah. It's rubidium, yeah, and no matter where you buy your rubidium, it's always rubidium, yeah. And so the photons that this device is emitting are always 780 nanometer rubidium photons. So it would be the ideal thing to integrate it into one of these platforms that are going, for example, for photonic quantum computing. Okay. Now it turns out there's a problem. Yeah, I mean the Rydberg atom is large. If you bring it close to a surface, like in a photonic circuit, there will be a strong interaction with the surface that produces some complication. Yeah? We can discuss how to solve this, but I want to ask another question, namely, do we actually need the Rydberg blockade for this effect, or can we get away with just normal two-level atoms that we excite from the ground to the excited state? Because we know if we do that, there's a dipole moment. And there is a dipole-dipole interaction between two atoms that are close by. Can we use that to do the same thing? And now you have to be very careful. If you have a medium of two-level atoms and you bring them very close, then they are interacting already, even if there's only a single photon. For the blockade effect, we needed two photons, right? We need two Rydberg atoms to make this excited state shift out of resonance. So clearly, this ensemble of atoms that are undergoing dipole-dipole interaction is different in nature. We cannot expect a normal blockade phenomenon from this right away. I will still tell you now that it's still a very highly nonlinear system, and how we can actually measure this is the topic of the next few slides. Of course, we need a density that is much larger than one atom per wavelength, actually over 2 pi cubed. Yeah? Then, if we are in that regime, the dipole-dipole interaction will exceed the natural line width of the transition. Okay? So we need high densities, and it cannot hurt to enhance the dipole-dipole interaction by either cavities, that's not what we do, or by dielectric environment, that is shaping the mode functions from pure plane waves or Gaussian modes that you are usually using in your normal experiments to something else. And I show you an example in a second. This dipole-dipole interaction, just as a reminder, you can think about it like this. Yeah? You have one excitation somewhere in the medium. It doesn't have a dipole moment, yeah? But if all the others are in the ground state, then this excitation will hop around, basically. Yeah? That's sort of the many-body aspect here. Yes? Just like in this movie, yeah? You see that if the population is either fully up or down, there's no dipole moment, but anything in between has a dipole moment, yeah? And that induces an interaction. Now, if you go to the weak excitation limit, let's say 1 photon only, yeah, then this medium is very nicely described by a Lorentz model, where you are basically treating this electronic excitation of every atom just like a little spring, yeah, where the charge is held to the nucleus. Yeah? So it's a very classical thing, actually. Yeah? And that explains also why the very first photon is already shifted out of resonance if your atoms are close enough together, okay? Because it's a coupled system from the very beginning, like a coupled system of antennas, for example. Yeah? So that is actually Theodor Förster. Yeah, I have to mention him every time I talk about this because he was a professor in Stuttgart, so in the chemistry department, by the way. Okay. So if you think about this light-induced dipole-dipole interaction, then you get a dipole field that is not a static dipole, it's an oscillating dipole. Yeah? It oscillates at the optical frequency. And if you plot the field of this Hertz dipole, yeah, it's a Lorentz model, yeah, this is how it looks like. Yeah? You have all learned about this in your electromagnetism lecture. If you put another dipole, you get a complicated expression for the dipole-dipole interaction energy. It has these nasty terms here that are due to retardation effects. But forget about them, yeah? Because if we put all the atoms, or the next neighbors, into this very small volume, smaller than lambda over 2 pi cubed, these retardation effects can be neglected, and we are back to the formula that also Lewis and others have shown for 2 static dipole moments. Yeah? It's anisotropic and goes like d squared over the distance cubed. And if you now think about an ensemble of these dipoles that are coupled this way, and you put them in 3 dimensions, you average over all orientations, the average is 0. If you put them in 2 dimensions, and the dipole orientation is like this, there's a redshift, or basically the energy is lower, yes, because of this dipolar coupling. If you put them in a chain next to each other, where they are all repelling each other, it costs energy, and you would expect a blue shift in the spectrum of this medium, okay? And I show you one experiment in 2D, or let's say quasi 2D, and one experiment in 1D, where we see a redshift and a blue shift. This is the first example. We take our thin cell, just the same cell as we used for the single photon source. And we increase the density for a short moment with the so-called light-induced atomic desorption pulse. There's rubidium sitting on the surfaces. If I apply a light laser pulse, this rubidium is taking off the surface. It increases the density for a short moment. This is the time scale here in nanoseconds. And if you then take a spectrum, a normal rubidium spectrum, and you measure the shift of that spectrum, you see that there's a redshift, yeah, of about 50 to 100 line widths. Gamma 0 is the natural line width of the D2 or D1 transition, which, of course, as the density vanishes, goes away again. Yeah? In this experiment, we achieved densities of n over k cubed. Wait a minute. Yeah, n over k cubed of 100. And you see that the shift is also on that order, yeah? 100 line widths. That's a redshift in the 2D case. Yeah? That's still not integrated in the photonic circuit. Yeah? Let's do that and make an ensemble that is very long, yes, and make a 1D chain. The way we do this is we take a photonic waveguide that is integrated on a chip, and this is a dielectric structure here and here, which guides the light along the chip. And we open it in the center, and there is a slot that has a width of about 50 nanometers only. So that's nanofabrication. We have a foundry on our campus, and we can ask the guys there to make it for us. Okay. This is the cross-section of this photonic waveguide. You see this is a dielectric material, silicon nitride, or silicon. And if you design it right, then the light that is propagating is concentrated in the gap. Okay, so it's traveling where the atoms can be. Okay. We actually use rubidium as a vapor, so we put this whole thing and immerse it into a rubidium vapor, such that the atoms can make their way into this gap, and we excite them there. We excite them by 2 photons. Actually, 1 photon we know already, that's a 780 nanometer transition. This one we shine from the top. By that, we can vary the population in this 5p state at will. Yeah, we put more or less light. We can say, let's have p population in the front of the guide, at the back of the guide, anywhere on the chip. In that sense, this is going to be a reconfigurable nonlinearity. Yeah, you can put it anywhere on the chip just by shining this light on and off. And then the guided light is actually a telecom wavelength, yeah? 1.5 micrometer. And rubidium is nice to us. It provides this wavelength. Now, I told you we are squeezing this 1.5 micrometer light through a 50 nanometer gap, which per photon enhances the electric field. And that is the essence of the Purcell effect. Basically, it's like this. Yeah? So you have this camel that goes through the needle's eye. Yes? This big wavelength photon you are funneling into this slot waveguide, which increases not only the field, it actually also increases the dipole-dipole interaction. Yeah? Because how is the dipole-dipole interaction mediated? It's the exchange of photons along this waveguide. Yeah? There is a Purcell enhancement of this interaction, and therefore also the nonlinearity. Okay. The experiment is fairly simple. Yeah? We have a Bragg coupler where we go into this structure and out of the structure again. Okay. Now, first thing to observe is if we measure a rubidium spectrum, yeah, at one line here, a particular line, you see it's fairly broad, yeah, a gigahertz typically. Yeah. Why is that? Well, the transient time and also the Doppler width of this is on that order. Yeah. So in terms of what you are used to from the cold atom world, oh, this is a very broad line. Yeah. If you are coming from the quantum dot people side, that's actually a narrow line, yes? They like a gigahertz line a lot, yeah? And what's more, huh?
Do you see shifts because of the surfaces, like from Kaiser?
Yes, there is a shift, but it's smaller than this 1 gigahertz. Yes, about 100 megahertz, yeah? What's more, if we are cranking up the power now, yeah? As we are funneling these photons through this narrow gap, we can saturate, and we measure this by broadening, by just power broadening this line. That's the width. You see it's 400 megahertz at very low powers, and then saturates, and here is about the saturation intensity and gets broader. Yeah? And if you look at this axis, the probe power that we need to saturate is 100 femtowatts. That's not a lot. Yeah? That's just a few photons, if you think about it in terms of the inverse bandwidth. Yeah? If you calculate this, this is a few tens of photons per nanosecond that is going through this device. Okay? So we are close, not quite, but close to single photon operation here, yeah? If you talk about the nonlinear behavior. So what happens if I drive this thing strongly is that I'm going away from this Lorentz model, yeah, the classical dipoles, to a situation where this shift actually goes away, because all these dipoles get out of phase due to a saturation effect. Yeah? So if we measure now this shift, okay, so first I should say we measure the shift for very low powers. It's the shift that is expected from the Lorentz model. The theory is actually this blue shaded line here. And if we exceed our saturation intensity, then the shift goes away. Here is a higher density. Now it's again this density per wavelength cubed parameter. That's the difference between these two plots. That's a little bit higher density than this one. And you see here we get again typically 100 gamma blue shift now, yeah, because we are choosing the polarization in this waveguide like this, such that the dipoles are repelling each other. That's about the saturation intensity, you know, or where we see that basically we have the highest response as function of the intensity. Yeah?
What is the difference between the red and the black circle?
Oh, this is just the example plot in the figure of the paper. We show this, I didn't put it here now, we show this one as an example spectrum. Yeah. So here is the summary. So as a function of density, we measure the line shift here to the blue. We again go all the way up to about 70 or 80 line widths. You realize we are not as dense as in this 2D experiment. Yeah? So that has technical reasons. We are not using Lyot, for example. We are just using a normal vapor cell. So there is room for improvement. Yeah? In the future, we could go even one order of magnitude higher here. Yeah? But you see that if you do this Lorentz model without Purcell enhancement, that's the dashed line here, you see that we are getting a shift or an interaction strength that is enhanced by a factor of 8 due to this camel through the needle eye effect, yeah, the Purcell effect. Yeah? That's an example. So I should actually sum this up and say, okay, now we have a medium, the properties of which, namely its resonance frequency, depends on the intensity. On the few photon level, let's say a few tens of photon level, we are changing the line, the resonance by 100 natural line width, I should say. Yeah? It's still a fraction of the total line width, which is much broader for us. Yeah? But at least, you know, that's the beginning of something interesting, I would say. Yeah? So meaning with like tens of photons, you can switch this resonance of this medium off or on, yeah? Which is the basis for switching light with light, you know. Not yet fully on the single photon level, but at the tens of photon level. Good, and this is just one example of what you can do if you are sort of bringing together the possibilities of nanophotonics with atomic vapors. Yeah? the traditional spectroscopy of atomic vapors, integrated in such a way. That's a real structure. Here you see these Bragg couplers, and actually this is a 3-port device. You can do a counter-propagating control laser, for example, and then do a saturation spectroscopy, if you like. If you send your light in here, and then you have the pump beam here, and then you look at the output here. That's a device. Once you have made this device, you don't need to adjust anything anymore. No mirrors around, no screws. Everything is stable. You can, as I showed you, by designing these waveguide structures, tailor the atom-light interaction at will to use this Purcell effect. You can also include cavities and so on. And it is a scalable technique. In one of the cells that we are using, we have hundreds of these circuits printed. Yeah? So one cell keeps several PhD students busy for some time. Good. So to summarize this first part, I showed you that in these slot waveguides, we can get on the order of 100 gamma line widths. We have seen this Purcell enhancement. We could get a density in units of wavelengths over 2 pi on the order of 7. In the previous experiment, we were with these Lyot pulses even at 100. And if you calculate now as a dispersive medium, what it takes to shift a propagating light field in phase by pi, which is what you need for a conditional phase gate, let's say, then with this kind of setup, you need tens of photons to do this. So there's still some way to go, because we would like to do this with a single photon in the end. And there are ways to improve the situation, either getting higher densities, getting even more fancy photonic structures like these so-called alligator resonators. I was told in in New Zealand or in Australia, alligators and crocodiles are different things, right? And so not sure whether alligator resonator is a good word, but huh?
They're also different here.
Aha, they are also different here. Okay, anyway, I'm not the expert on this, so.
You wouldn't live to tell the tale.
Okay. Anyway, what's important are the T's here, yes? And if they are periodic, then it's like a Bragg reflector, and you make up something like a cavity to increase this Purcell effect even further. Okay, this is the team of people. It's actually some time ago, and I should mention that Hadise Alayan at Purdue is a team member and still attending all the group meetings with us, and so does Charles Adams. And I should mention, it's actually an older picture. Florian has graduated, Arthur has graduated already. These guys have been bachelor and master students only. The current team that is working on this is actually Annika and Max and Felix here. And Benjamin is the guy who's making the structures in the foundry. Good. That was the first half of the talk. How much time is left?
6 minutes.
6? Oh, that's not a lot. Good. I wanted to talk about molecules as well. Actually, I changed the title slightly for this part. Namely, I talk about charge-dipole interactions between Rydberg electrons and molecules. Yes. We're talking about dipole-dipole interaction. It falls off like 1 over r to the 3rd power. But if you think about the interaction of a charge with a dipole, it goes like 1 over r squared, even more long range. That's fun. We should do it. Okay. So this goes back to a discussion I had over time, many years now, with Hussein. An experiment that we started on nitric oxide several years ago, about 3 years ago. And Hussein and Rosario and Janine, they came up with this beautiful idea to make molecules of molecules that are bound by the charge-dipole interaction. Okay. Nitric oxide, NO, has a dipole moment. It's a heteronuclear molecule. It's a small dipole moment. It's 0.16 dBi, which is actually smaller than this so-called Fermi-Teller limit, where you get a bound state, from which on you get a bound state. Still, there exists NO minus, yeah, so the anion. So if you scatter an electron from that nitric oxide, you will get an, I would say, unpredictable interaction at first. Yeah? So you have to measure something. So the question is, can we observe these objects? Okay. And I should tell you, but I have no time to go into the detail, that actually our motivation initially was very different, namely to detect the NO in the human breath as a medical diagnosis thing. That's this thing, but ask me about it later. So our measurement principle is the following. We take NO from a gas bottle, send it through our setup. We excite it actually with 3 photons to the Rydberg state. This Rydberg state collides with the background gas. The charges get released. You get an electron and an ion. If you apply a small electric field, they are pulled to some electrodes and we measure a current. Okay, that's this thing. These charges are going to be measured with 2 plates, just a capacitor, and we measure a current. That's an optogalvanic spectroscopy method, I would say. Yeah? Some sort of variant of this, sort of old-fashioned, but very, very sensitive, as you will see. This is the cell. You see we are filling NO in here, and it flows through to the other side. We have an electrode here, that's the gold-plated thing here, and we are exciting this from the side. Okay. And you see it's important to have a transimpedance amplifier, TR, very close by to your current source. Okay. And the fun fact of this is that these TRs these days, using fancy pseudo-resistance techniques that I cannot explain to you, we have a collaboration with some guy in the electronics engineering department that is making this chip for us. They have a noise floor of 10 femtoamps per square root hertz. Yeah? That's a small current, right? So if we send in our lasers, our 3 photons, yeah, first of all, we need a 226 nanometer laser. That's, of course, a broad transition, yeah, because it's a thermal ensemble. Yeah, we have a large Doppler width, yeah, several gigahertz here, actually almost 3 gigahertz. But then this UV laser is a CW laser. It selects the velocity class. If we then excite it to the next higher lying state, which is this so-called H state here, the line becomes very narrow if we are scanning the green laser. And then finally, we go to the Rydberg state with the 835 nanometer, and we get some spectrum, some Rydberg spectrum. Actually, you see the currents here. Yeah? Already here we get picoamps, and then up here we get nanoamps. Yeah? Remember, femtoamps per square root hertz is the noise level. So we have a very good signal to noise. I can go into the detail of the molecular physics. Maybe I skip this. There are various channels, of course, for the Rydberg excitation. This is how a Rydberg spectrum looks like if you take it. You see there are actually 2 series overlapping because of different rotational states now of the nitric oxide ionic core. There's one for the rotation quantum number, that's actually Hund's case D, yeah, in the Rydberg state, 5. And you can assign these numbers here, and you see principal quantum numbers go up to 60 or something. And there's a second series here, which is the other rotational quantum number of the inner core of the molecule that is excited, and we go up to, yeah, again, 60 or something like this. Yeah? So now let's look at one of these lines, maybe this one here, and we see there are 2 lines here, 61 belonging to the n equals 3 and the 41 belonging to the 5 rotational quantum number, and apply an electric field. And we see a Stark map, yeah, of this NO Rydberg molecule. And you see familiar stuff, yeah, like this is the hydrogen-like fan that spans in the electric field. And if you have good friends, not only Hussein, but also Stephen Hogan and Matthew Raymond, his student, then they can come up with a theoretical prediction for this Stark map. And it fits fairly nicely, actually, I must say, even in some details like this. Here's another measurement. This is a measured Stark map. It takes about an hour to measure this. Yeah, and you see it's basically no noise. Yeah, it has a current here of half a nanoamp. And you see the high L states. And now you see also, again, the hydrogen-like zero quantum defect Stark fan. And you can see that this kind of measurement is well suited to measure the quantum defect of these states. Yeah? The H state, for example, the G state, and the F state. Yeah? If you come from a rubidium or an atomic site, the quantum defect already for the F state is negligible. Yeah? It's very small. Here it is sizable. Why is that? Well, a rotating molecule is just a bigger object than an atom. Yeah? Now these quantum defects are going to be dependent on the rotational quantum number, yeah? Because the faster you rotate, the bigger the thing gets. Yeah? So you have to do some systematic measurements of these quantum defects as a function of this rotational quantum number, 4 in this case. So work in progress means we are taking a lot of these Stark maps right now to just measure those quantum defects. That's a prerequisite for stuff that is going to happen soon. So, but I want to point out this state here is the one that has no dipole moment along the electric field direction. That's why it is the most narrow line in this spectrum, because we have a little bit of inhomogeneous electric field. So we get a narrow feature here. The line width of this is about 100 megahertz. And we can now measure the pressure shift of this line, okay, and the broadening. Now, this is a very old topic. Yeah? Measuring pressure shifts and broadenings started actually the whole field of Rydberg spectroscopy in the 1930s. Amaldi, Segre, Fermi, and others pioneered this by looking at Rydberg lines in discharge lamps. Okay. And that's how the concept of the scattering lengths actually was introduced to physics in general, actually. Yeah. So you get an interaction of the Rydberg electron with this polarizable atom, that is maybe your background gas, that is proportional to the density, yeah, and to the scattering length. Yeah. If the scattering length is positive, you get a blue shift. If it's negative, then you get a red shift. Okay, so here is some data from this Amaldi-Segre paper. Yeah? This is the interaction in 300 gigahertz units here. And this is the density. So they were working at atmospheric pressures. But you see a nice linear behavior. And it doesn't matter whether this Rydberg electron came from a potassium or a sodium atom. Yeah? It's just this electron is so far away from the core, it interacts with this polarizable background. And in this case, it was a hydrogen molecule. Yeah? Here's another plot, which I find interesting, from a German group in 1934. They measure this red shift and the blue shift as a function of principal quantum number for background gases of different kind. Yeah? Helium, blue shift. Neon, no shift. Argon, red shift. Okay, and that just tells you this scattering length can be anything. Yeah? Now here's our measurement. The interaction of rubidium, so these are older measurements that we did some years ago, just as a reference now. As I said, doesn't really matter where the electron comes from as long as you understand the orbital. Interacting with argon, and you see there is a little bit of redshift as in these old measurements. And here you also see the broadening. Yeah? The broadening in this case is actually on the order or a little bit smaller than the shift. If you take a background gas that is nitrogen, okay, you get almost no shift here, as also in these old days was already known, and some broadening here. And now we do the same experiment with nitric oxide. To my knowledge, that was not done so far, because nitric oxide is not something you pour into your discharge. Yeah? It's a reactive gas. Okay. So what we see there is a shift that goes to the red. Actually, that's all the same scale. So it's almost like in this argon case here. Yeah? But what you observe is that the broadening is tremendously larger than in the other cases. And what is new here now is this is a C2 interaction, not a C4 interaction. Yeah? So it's like a charge-dipole interaction, which is stronger than the interaction of the charge with an induced dipole. Yes? So we see this just by eye, yeah? Let's say. Yeah? We get a very large broadening. Why is that? Why do we actually see a broadening and not just a very strong shift? The reason is simple. Yeah? It's a thermal gas. And the distribution of the rotational states is thermally populated. So our perturber in the Rydberg orbit, although we know this orbit very well and know all the quantum numbers, this perturber here is in a mixed thermal state of all possible rotational quantum numbers, described actually in Hund's case A by the quantum number J here, yes? And you see, yeah, in principle, we have a mixture of all these different rotational states in our signal. And now, of course, what needs to be done in the future, and that brings me to the end, that's already the outlook, Louis, is that we are selecting a single of those rotational states. How can we do that? We need to modulate a property of this rotational state, for example, a rotational transition, and demodulate it with a lock-in amplifier. If we have enough signal to noise, and I hope I convinced you we have a lot of signal to noise, we are quite confident that we can single out every single individual rotational state and then measure not the ensemble average shift and its broadening, but individual lines that are depending on the rotational state. And that brings us then to this figure from Hussein and Rosario's paper, where they predict actually binding energies for those no-no molecules. So this is Hussein's invention, a molecule of molecules, which are on the order of a few hundred megahertz. Yeah? This resolution we certainly have. Yeah? And so we are discussing this also as we are here. Summarizing, we do high-resolution free-photon Rydberg spectroscopy with these no-no molecules. We measure the Stark maps, and we do systematic studies of all the quantum defects there, and have detected the pressure shift and the broadening for the thermal ensemble, and hopefully in the future we can single out a single channel there. And I should not end without thanking the team. I should say this is really the work by Fabian Munkes. Yeah, he is an outstanding PhD student. Harald and I, we have the pleasure to supervise him. And the other guys, they just started their bachelor thesis just a few weeks ago, and Alex started the master thesis also just a few months ago. Thank you for your attention.
Thank you, Tilman. So we have time for a very quick question, if there's any.
I just have a technical question. I was amazed about how well you can, put the light into your nano structure. And I was wondering how much of the light field travels in these dielectric rods as compared to what's really inside the slit? And how does that go into question. Impedance matching?
Okay. So the question is about this structure here. And I showed you this cross-section, this one here. So if I calculate the Purcell effect in here, just locally there, yeah, I get an enhancement of about 35 or 40. What we measure is 8. And the reason for that is, that there is interaction also with these other, with the other evanescent field available. So yeah, in that sense, not all the light is going through that channel. Yeah. See that, but we see an average effect over the whole mode that is still a factor of 8. That's the measured value. Yeah.
Thank you very much. So I think we should move to Igor's.
Let's